Hello guys, let's go ahead and get started. We're going to be doing this recording a little bit different. As you can see, all of the answers have already been placed on the review guide, and I'm doing this because I'm really not recording from home. So instead of using my document reader, I'm actually using my iPad. So for the first one, it's a nebula. A nebula is a huge cloud of dust and gas where stars are formed. We say gas and dust and gravity, gas and dust and gravity, and then all of a sudden, boom, and a star gets formed. Now, a star. What is a star? Just like when I said boom earlier and a star is formed, it's because the star went through nuclear fusion, okay? Because hydrogen atoms converted into helium. So now instead of just having hydrogen, we have helium as well. So then these are the stars. Here's the example. Again, a star is a ball of hydrogen and helium fueled by nuclear fusion reactions in the core. A galaxy, what is a galaxy? Well, we said star is a ball of hydrogen and helium. So then galaxies are made up of all of these collection of galaxies. Collection of hydrogen and helium balls, which are stars. So then we have a collection of stars held together by gravity. So talking about gravities, we have three different main type of galaxies. Spiral galaxy, that's like our Milky Way galaxy. A spiral galaxy has arms at the center. There's a bulge. That's where we find the old stars, and then on the arms we're going to find the younger stars because that's where we have most of the gas and dust and gases. The second one is going to be the elliptical galaxy. As you can see right here, at the middle of an elliptical galaxy, we see a lot of old red giants. And then, of course, there's still a little bit of gas and dust, which means that the elliptical galaxy is one of the most oldest type of galaxies. They have very little ingredients for new galaxies to form, for new stars to form, which is the gas and dust. The irregular galaxy, as you can see, has no regular shape, and it has a lot of gas and dust, so that means that there's an opportunity for many, many, many more new stars to form. So the irregular galaxies, are some of the youngest galaxies. Now, our galaxy, which is called the Milky Way galaxy, is a spiral galaxy. It's a spiral-shaped galaxy. Our solar system is located at the edge of a disc-shaped galaxy of stars. Let's go to the next one. This, I'm going to go only over the HR diagram. We're not going to answer the questions. We will practice with the questions in a little bit. But when we're talking about the HR diagram, I want you to think about it as a graph. We have the temperature, which increases from right to left instead of left to right. And then the luminosity or the brightness is going to increase from the bottom to the top. We also have the spectral class that is included in some of these graphs. If you look at the spectral class, usually you'll see letters that represent the temperatures of each of those galaxies. So if we're asked which type of stars do we have on the upper left-hand corner, we're going to say bright because they're very bright, and very hot because they're found on the left hand and on the upper left-hand corner. Now, the ones at the bottom, we have a high temperature. You see here 50,000, but they're very dim because they're not way at the top of the chart or of the graph. We have the dimmer ones here at the bottom. Then if we look at the bottom right, we have the dim and the cool because they're at the bottom. At the bottom, we find dim and cool because they're on the right-hand side. And when we look at the upper right-hand side, they're very bright because bright, the higher we go up to the top, the brighter the stars are. And as we move to the right, the cooler that they get because their temperature is lower. Over here we have an example, or we have an image of the Milky Way galaxy, and it's asking where is the sun located. I put the sun right here on letter D. Now let's look at those questions, and please do me a favor. If I'm speaking a little bit too fast, go ahead and pause the video so that you can listen for the information, or so you can go back if you need to. It says the universe has many different components, which list places. I'm sorry, let me go ahead and get it closer. The universe has many different components, which list places four components of the universe in the most likely order from smallest to large. So then I put right here, yes, we have planets. So smallest to large planets, yes, is good, but stars also. And then we have the galaxy, we're going in the right order, but nebulae or nebula are supposed to be uh, before stars, okay, because that's where stars are born. Or actually after stars, I'm sorry. So it's planets, stars, and then nebula. So that one's wrong. The next one says nebula, and then stars, and then planets. So then right here, no, this is going to be wrong. Nebula, yeah, in nebula we find the stars, and then the planets, no, planets are a lot smaller, okay, than the stars. We have galaxies, stars, no, we find stars within the galaxies. So the correct one is planets, stars, nebulae, and galaxies. And here we have the order if they're asking us from the asteroids. So we have asteroids, moons, planets, stars, nebulae, solar system, galaxy, and universe. The next question says, with the use of the Hubble Space Telescope, scientists recently discovered a giant runaway star. It is 90 times larger than the sun and is very hot, blue-white in color. Why does the sun appear to be brighter than this runaway star when viewed from Earth? So all of the other information doesn't matter. What matters is that why does the sun appear to be brighter? And remember that it is because the sun is closest to Earth. So then the other possible answers, those are wrong. Let's go ahead and go to the next section. It says 4 students are asked to describe a nebula and a star. Their responses are shown in the table below. Once again, I put up here gas and dust, and I should have put over here nuclear fusion of gases. So then right here, the first one says a collection of hot gases for a nebula. No, it's not hot gases, okay? This one's what we're going to focus on, the gas and the dust. And then let's go to the next one. A collection of hot gases. Nope, we're going to say no. A collection of dust and gas. Remember, gas and dust. And with gravity, it's what's going to form stars. And then for the description of a star, it's a sphere, temperature, great enough to go through nuclear reaction. So the correct answer is going to be letter H right here, letter H. There's only one question there, so let me go to the next one. It says 2 stars are identified on the HR diagram below. Based on this diagram, how do characteristics of star 1 and star 2 compare? So first of all, when I come to star 1, it's very hot and bright. When I go to star 2, it's dim and it's not so bright. So it says, based on this diagram, how do characteristics of star 1 and 2 compare? So we already kind of like saw that comparison, but let's look at the possible answers. Possible answer 1 says star 1 is cooler and less brighter. Star 1, less cooler. Nope, it's not cooler. It's actually hotter than star 2. Now, G says star 1 is hotter and brighter. Yes, we see it way up here, way up to the upper left. And the 2 is close to the right and close to the bottom. So star 1 is hotter and brighter than star 2. That is correct. And I would put a question mark right here. Let's look at letter H. Star 1 is cooler. No, we see it. It's over here at the top. So it's actually hotter. So I X cooler out. Now, letter J, letter J, star 1 is hotter. Yes. And less bright. No, it's a lot brighter because it's over here at the top. So then that was it for 20. Let's go ahead and go to number 9 on page 32. Which of these changes would likely occur if the rate of Earth's rotation on its axis increasing? So then think about it. We have the Earth rotating, and if it goes a lot faster, we're going to have shorter days, okay? Kind of like if you run faster than slow, when you run faster, you're going to travel the clock is not going to move as much That means you're going to take less time to get from one place to another. So the length of the seasons don't have anything to do with it. So that's why I X'd out seasons. The length of the seasons would be longer. We X that out. The length of the day would be shorter, kind of like the distance that you would take to travel would be shorter. Letter D, the length of the day would be longer. Nope, that's not going to happen if the rotation moves a little bit quicker. Let's go to the next one. Again, another HR diagram. So then right here it says, based on this diagram, which type of stars would belong to spectral class M and have the highest luminosity? As you can see, remember that I say spectral class. Here, they labeled it, or they labeled the graph with spectral class and not the temperature. So then right here, spectral class M is right here. I can go from top to bottom. So then it says which type of star would belong to spectral class M and have the highest luminosity. So we're gonna go all the way to the top. Okay, so we end up with the supergiants over here. These are part of the supergiants. So it is going to be letter J. Let's go ahead and go to the bottom. Why does Earth get more energy from the sun than from all the other stars in the universe combined? Well, why do you think if you get closer to a barbecue pit, you're going to get a lot more of that heat than if you move further away from it? So then, why? Because the sun is much larger? No, remember the sun is a medium-sized star. The sun is much hotter. No, the temperature is not even that hot. The sun is much more dense than other stars. No, we don't compare the density of the stars, or we say that actually it's a medium, so I assume less dense. And letter D, the sun is much closer. There we go. That's a better answer. So the correct answer is letter D. Let's go to the next one. 15. The Hertzsprung-Russell diagram shows how the sun is classified among the stars. Here we see the sun. The sun's always going to be aligned with number 1 because that's what we use as a comparison. So then the sun is at 1 luminosity, and then it's a spectral class G. It ends up right here in this section. So spectral class G gives us a temperature of, let's say, maybe 5,000. Yeah, close to 5,000 because it's near the 6,000, and the sun is 5,800 and some, if I'm not mistaken. It's very close to 6,000 Kelvin. So then a star that is several thousand times brighter than the sun with a temperature lower than 4,000 K would be classified as, so then right here we have a main sequence star in spectral class B. And actually we circled right here the range where it's about 4,000 degrees Kelvin. So then right here we need one that is similar to Earth but a lot brighter, or actually less. It's at a 4,000. I was thinking it was at 5,800, but since I saw the dot I got confused. So it's at a 4,000 K but a lot brighter. Okay, but a lot brighter than the sun. So then it's going to be right here, which is spectral class K. So it's going to be this one. Okay, let's go to the next one. Which of these correctly compares the masses of different objects in the universe? And I'm going to go all the way to the bottom. A star, the masses of the object correctly compares the masses of different objects in the universe. Oh, okay, so it's not giving us any order. Here, I thought it was going to ask us for the order, but no, it's actually which one makes more sense. So a moon has less mass than a star, yeah, and more mass than the planet. Nope, the moon also has less mass than the planet. A planet has less mass than a galaxy, yes, and the galaxy more mass than a star. So then planet, less mass than a galaxy, yes, and more mass than a star. No, the planet doesn't have more mass than a star. H, a galaxy has less mass than the moon and more mass than a planet. No, a galaxy doesn't have less mass than the moon. It has more. The last one, a star has less mass than a galaxy. Yes. And more mass than a planet. Yes. So it's going to be letter J. For 49, the Hartsburg-Russell diagram below shows how the brightness and surface temperature and color of stars are related. Okay. So then we have the brightness going from bottom to top, surface temperature from right to left, and the color of the star. Here we have the white dwarfs, yellow from the from the main sequence. There's different colors, and then we have the red giants and then the red supergiants. Which of these observations of Bernard's star is most likely accurate? Here we have Bernard's star right here. Okay. Bernard's star is less bright than the sun. Yeah, because the sun's over here. It has a surface temperature below 3,800 K. Yes, Kelvin. So then, yes. So I believe letter A is the correct answer. Letter B says Bernard's star is less brighter than the sun. It is less brighter than the sun. It has a surface temperature about 3,800. It doesn't. It's within the 3,800 range. Letter C, Bernard's star is brighter than the sun. No, it's less brighter because it's more towards the bottom. Bernard's star is brighter than the sun. Again, nope. So then the correct answer, it is going to be letter A. It says the Milky Way galaxy is described as a disk of stars orbiting a central point on the disk. Which of these best explains why people on Earth cannot see the entire shape of the Milky Way galaxy? Well, guys, like I mentioned before, when we are at liberty, we cannot see the whole building. In order for us to see the whole building, we would need to move away from it because we're part of it. So the same thing here. If we wanted to see the whole galaxy, we would need to move away from it. So that answer would be letter A. Right here for number 27, it says the HR diagram is shown. The diagram shown is divided into 4 sections. So we have the 4 sections right here. Which section of the diagram includes the coolest and the brightest star? Remember, we did some of the labeling a little while ago. So then the coolest are going to be the ones that are towards the bottom. Okay, coolest because they're not as hot. And brighter is going to be, cooler is going to be from right to left. And then brighter is going to be from bottom to top. So then right here, there we go. Cool and bright. So these are cool because I'm more towards the right, and I'm bright because I'm towards the top. So it's going to be section 2. Number 39, which statement best describes a galaxy? A cloud of gas? No. A system of billions of stars, gas and dust held together by gravity. This one sounds very good. Letter B. A ball of plasma that experiences nuclear fusion in its core. No. A mass of dust and ice that orbits. No, this is going to be a comet. Okay, so then the correct answer is letter B. And the next one, the spectral classes of 4 stars are shown in comparison with the HR Russell diagram. Based on the information, which star is more like the sun? If I look at the sun is right here, and I could say that the sun is a spectral class G. So then I come over here to the spectral class. It goes from O, B, A, F, G, K, M. This one right here, star 3, is going to be more like the sun. Let me see if there's no other. There we go. Let's go to this one. Most stars in the universe fit into one of 4 areas on the HR diagram. Which area of the diagram represents the white dwarfs? So then if we look right here, this is where we're going to find the white dwarfs. So it's going to be area Z. Remember that right here we have a range of colors when we're talking about the main sequence, but they're talking about the dwarfs. These are not dwarfs. Number 16. In November 2013, an object orbiting the sun seemed to disappear behind the sun. When a satellite did not detect the object, astronomers thought that the object had been destroyed when it passed close to the sun. However, when another satellite detected a small bright object with a fan-shaped tail, astronomers proposed that the object was not destroyed. What type of object were astronomers likely observing? And it was the comet, guys. Okay, if you remember, the comets have a tail, and the tail is going to be kind of like be trailing. Okay, so the correct answer is letter F. Now, for this section, it says the sun. Our sun is a medium-sized yellow star, so it's yellow, not orange, found near the edge of a disc-shaped galaxy of stars. The sun is the brightest star seen from Earth because it is closest to Earth than any other stars. So that this information could have helped us a little while ago with the other questions. So then it says right here, we need to put whether the statement is true or false. The sun is the planet located. A, it's not a planet, it's a star. So that's false. 2, the sun is located near the edge of the disc-shaped Milky Way galaxy. That is true. 3, the sun is the third closest star. No, the sun is the closest star to Earth. So that's false. Number 4, the sun appears brighter than any other star in our galaxy. Yes, it does, and it's because it's closest to us. Number 5, the sun is medium in size compared to other stars, and that is true. We're not going to cover light years, so I remove that one. Let's go to this one. Again, the HR diagram. Bernard's star is about 5.9 light years from the sun. The star has an approximate temperature of 2,800 K. Based on the diagram, what spectral class does Bernard's star belong to? 2800. This is 24. So then right here, if we look at this one, this is going to be a lot higher because look at the difference between the two. So then we're going to say it's a spectral class M. For number 5, a student learns that the sun is classified as a medium-sized star and that many stars are much bigger and brighter. However, the student observes that other stars look very dim, even through a telescope. Why do other stars look much dimmer than the sun? And this is already the third question that is giving us a different type of question, but they just want you to know and to be aware that the sun is much closer to Earth than other stars, and that's why we see it a lot closer. So then we're not going to go into that. So then that'll be it, guys. I'll see you guys tomorrow.